Oh, really? It helps. No, I mean, it's like, once you have, you will be given. If you have a track record of successful proposals, you can. Synthesis awards, some kind of award, and every committee feels better, and you're no risk person, and you have another.
Okay, I think I'm going to not hear myself in an echo because that's way too confusing. Hypothetically, we are now live streaming to YouTube from the Zoom, and I've, to be even more confusing, sent you a link to the very live stream that you're going to be 45 seconds delayed on. Which you should probably not listen to risk being as confused as I am listening to myself on a minor delay.
That sounds absolutely terrible. Yeah, I won't open it, but thanks for setting it up. Do you want to? Oh no, it's for later. Yeah, you can post the second link in the.
Yeah, but you might as well. I should stop again listening to myself. You might as well open it up real quick to make sure this is how you want things to appear. At least from the standpoint of like, this is, you got yourself on the right. I can try to make it where you have the speaker at the slight right, which might be a little bit nicer. Give me a second. How do I change the view?
Oh yeah,
standard.
It's quite.
There we go. It is quite delayed. And can you say something to see if it changes the active speaker back to you?
Oh, of course, yes.
Okay, it does. Okay, we're good.
Okay.
What, sorry?
Didn't said anything.
Yes, because he's on said YouTube link. He's seeing his own screen on YouTube.
Wait a bit time.
Oh yeah, that's fair. Yeah, you're currently live streaming everything to YouTube proper.
Yeah, I know that. Yes. Can I close the YouTube now and go?
Yeah, you can close it. Yeah, if everything seems good to you, then I think we're good. I'm going to start recording just for the sake of we don't lose it. We've still got time because lunch goes on another 5 minutes and people naturally spend longer at lunch to get back. But wanted to make
I don't
sure
want
we
to
were
disrupt anyone from like getting his well-deserved lunch. So
indeed, you're sharing your entire screen. I think there's you're sharing your entire screen thing on your end. If you want to move that, again, it's very minor. Oh, there's like a box there.
No?
Okay, I think you're good. I'm gonna also click record here. I'm gonna give you permission to record to your computer just in case something goes horribly wrong.
Okay.
Which requires you to also join Zoom and be confused.
Where do we set that in Zoom? Oh, you're talking to someone else.
Oh, yeah, sorry, talking to Sarah, who's here locally, so we can also record the Zoom just in case something goes wrong, which we're recording it in like 3 different ways. So at minimum, one of them will work. Ideally, all of the things work, but just in case. Yeah.
I also have a record button if you want me to click it, but yeah.
So if you misspeak once, there will be many copies.
But we can edit it in the worst case.
This talk is never going to get lost.
I need to log into a different Zoom account because I'm logged into my Illinois Zoom and not the MIT Zoom. 1 second.
Recording in progress.
Okay, it is now also recording to the cloud. So we have all the things. I'll be back. I'm going to get a snack from the back. Critical. We're going to start in like 5 minutes. You can continue to casually chat for 5 minutes. Now it's on.
Hello, Zoom people. Can you hear me?
We can. Great to hear you.
Can you try speaking again? Maybe a little louder.
Sure. Here I'm saying something.
Okay, that's good. Thank you.
Understand?
Yeah.
Hi, Valentin.
Something into the mic.
Because they're the two for the second one.
Manuel, do you want to do 2 talks in a row, or this talk and then the next talk in an hour?
Good question. Jet, I didn't add your slide yet, but on that, I mean, if you want to present your slide or so, then we could, yeah, do both in a row.
Yeah, whatever. We can do it either way.
Might be easier for you to set up, right?
Yeah, I can do either. That's fine.
Okay.
Then I propose we do 2 in a row. So while we have Zoom working, we keep that. if it's okay for everyone. Welcome back from lunch, everyone. I hope you could find lunch. We have 4 more talks in the afternoon, and to simplify things with Zoom, we are going to swap the last talk, and it will be the second talk. So we'll have 2 remote presentations in a row. While the thing still works, I hope it will keep working for the hour we have.
And I'm talking into this just to test the second mic.
And we forgot to actually check if it works, but they can hear us. They can also see the room through that camera. Please wave into the camera. That's where we should have taken the picture.
Fair point.
Anyway, can you please wave again? I'm sorry about that, but we need a cool picture for the website. Thank you. So, Manuel, can you hear both me and Billy?
Hello again.
Yep, perfectly clear.
Great. So if you have questions in the end, please wait until one of us comes to you with a mic. Otherwise, they cannot hear us. With that, I'll hand it off to Manuel to talk about blasphemy.
Okay, thanks. Yes, so, well, nice to be here. So my first talk is about what I've been working on during the last summer, how to improve the performance for linear algebra for Enzyme. I've been working with a few more people, which are mostly in the room, I assume. So yeah, let's get started. I mean, most of you, I assume by now, have seen these images before, like how the normal compilation pipeline goes of classic AD tools. You first differentiate your source code language, you lower it, optimize, and generate some code. That's pretty old. So we have this case study here. Also, please interrupt me if someone ended up showing it before, but like just in case, I want to show it again. Where we do have a function which is compute in O of n and call that inside of a loop, which again is O of n being to n square. And we have a nice compiler optimization for that, which allows us to reduce the whole function to O of n. So, well, that's pretty nice. It does work also if we have a classical compilation pipeline where we first do the optimization and then call AD, because here we have a simple O of n loop. So even in the reverse pass, we end up with O of n. However, in the like previous slide, I've shown how some of the old AD tools work, and they do AD on a source code level, making the source code a bit more complicated. So classical optimizations don't grasp the full concept anymore, are not able to optimize properly, and we end up with O of n squared. So that's a bit sad. So that's why now we want to do the typical lowering of LVM, optimize there, call enzyme, and afterwards optimize a second time. So yeah, we have a couple of benchmarks which we ran in the original paper, and here we see this performance gains. So the point is these performance gains mostly stem from classical compiler optimizations. And my talk then was to look at, my work was to look at, well, how do the compilation pipeline works for linear algebra heavy code. In Julia especially, where I looked at, we have the case that all the matrix and vector operations are lowered to BLAS calls, either OpenBLAS, Intel MKL, or whatever library your Julia installation uses. And they are pretty well optimized. They are multi-threaded. They are tailored towards your hardware. And some of them, like Intel MKL or so, are closed source. So for a tool like Intel, that's obviously for a tool like Enzyme, that's obviously challenging, right? So what do we do about it? in the past, we had a fallback for the Julia side where we literally recognized every call to a BLAST library and replaced it by a call to a precompiled open BLAST library. We have simplified that library, so it might not be optimized for your hardware because it's one which we insert. It only uses a single thread, and most of the times it now just works because we have the LVMIR for your BLAST calls. It's just a performance loss which you get in exchange for being able to differentiate BLAST. So there are some challenges with that. One example is correctness. So we have one of the issues in enzyme.jl, which was about BLAST having a fallback having a short circuit 0 path. So effectively, it was checking if one of the dimension was 0, and in that case, it realized it didn't really have to do any work, so it was returning A early. That was correct for the primal. The issue is it's not correct if you want to compute gradients. So what we had to do is take our Open BLAST implementation, which was already slower than the Intel MKL version, like remove all those fast passes, just like making it a little bit slower in the special case. So that was really a great experience. We also had some user warnings because, of course, like if we surprise them by replacing the BLAST library, we might want to warn them, right? So just that they are aware of what's happening. So people were showing up in the enzyme.jl issues and asking about what's up with this performance issue, how can we fix it? And there was another performance issue. I mean, Julia has a couple of libraries to like work nicely in multi-thread environments, and now here we are with Enzyme, a popular AD library, and replacing the multi-thread BLAST library with a single thread one. So that's the speed up they got when they used Enzyme in the past. And obviously, it's not great. Like, that's not what you expect as a speed up if you have 48 threads on your system. How can we do better? I mean, in AD, you generally have these custom rules. They are quite common in the Julia ecosystem, especially. So some people start to write custom rules just so Enzyme doesn't have to use its fallback. And these rules were actually a lot faster, like even for really simple BLAST functions like dot, which effectively is just like you take two vectors, multiply them, and add them up. So there's no really heavy math involved. Even there, we were 6 times faster in forward mode and up to 60 times faster in reverse mode. So that's a significant speed up. And we could imagine that for real functions like matrix vector or matrix multiplication, such a speed up might be even larger. So of course, it would be nice to have such enzyme rules for all of the linear algebra, right? So what we did instead, since we are inside of like the compiler, we are inside of Enzyme, so we can do it slightly better even than just writing custom chain rules. We can write enzyme rules. And that's the example I created for dot. So effectively, we do match the function name of like dot. We see if there's a BLAST code with that name and the right number of arguments and all of these. And then we insert, depending on which, with respect to which parameters you want to differentiate, another call to another BLAST library function, expy in that case. So that means we don't replace, if we go for this route, we don't have to replace the original BLAST library. We just can call certain other BLAST functions to compute your gradients. And doing that inside of Enzyme was another 2 times speed up. So instead of like 6 or 60 times, we now were 12 to 120 times faster than our fallback, which I guess makes sense if you now have highly optimized libraries. These rules didn't really look great, like especially if you have more complex one, like sparse matrix vector. You have like a lot of parameters with respect to which you might differentiate. So they're not super nice to write, but I mean, it's worth for the performance gain, I would say. And so we obviously did some benchmarks on these results. And now it kind of happens as you would expect it. We do get significant speedups from using multi-threaded CPUs. Here we also only have pretty small benchmarks because that's not a limitation of our new implementation. It's just our fallback when doing these benchmarks used to crash if our matrix sizes were too large. So it wasn't only slow, but it also was not fully supported. The one point which I have to point out is a lot of these speedups from using multiple threads were not particularly due to using multiple threads. You can see there is some speedup on the right, but a lot just stemmed from the fact that we didn't use our own Open BLAST library, but use the proper Intel MKL or whatever faster version you had on your side. So yeah, we should probably rerun those benchmarks to get some more reliable numbers, but it's definitely a nice improvement. We also have been doing some comparisons to other AD tools. So what we've seen is compared to Zygote, yes, we are slightly faster. We are not faster in every case. So there's still a small performance gap here on the right side, which you can see, which we haven't figured out yet in the multi-thread environment, why we have such a gap here. So it's still some work in progress. And yeah, so looking at these, what we developed is we have a cool code generation tooling, because writing all those rules by hand turned out to be completely unfeasible. As an example, even a rule for inside of enzyme to handle matrix-matrix multiplication was more than 1,000 lines of code. So we use TableGen, which is an LVM tool to generate code based on the rules which I've been showing on some previous slides. And that made it a lot nicer. So we now had like 3,000 lines of code to describe how we want to generate the code. And the actual generated code was 3,600 lines. So it's not a great amount of lines which we saved, but it's still like the logic is easier to handle. So I would say it's worth it. On the right side, you can see the math of like how much you can save. Yeah, about the features which we have, it's mostly tailored towards reverse mode, which was just motivated by the Julia side, mostly using reverse mode AD, just because for most problems it's more interesting. We do have runtime activity, which means if you are not sure at compile time whether you want to differentiate your code with respect to a certain parameter, then you can decide that at runtime. There's a small performance penalty because we can't optimize that well. So we might do a little bit of extra work, but it's a fair overhead. And yeah, so we have a couple of functions which are supported, mainly, namely scal. So like scalar times vector dot, which is vector times a vector, xpi, which is slightly more complicated, gemv, which is a matrix vector, spmv, which includes sparsity, and gem, which is the classical matrix. Technically, we should be able to support more cases. These were just like the most urgent ones. So if someone has some time and can contribute more test cases, we would love to support more functions. That's, I think, one of the blocking things. And yeah, thanks to Saxon for writing some infrastructure which made the testing a lot nicer on the Julia side. So I mentioned on the previous slide that we looked at comparing Enzyme now with our new setup to Zygote, and that we weren't completely sure of why we were slower. So we did a little bit of benchmarking later on, and especially DTune Profiler turned some interesting insights. So especially if you do matrix vector or matrix operations, you would assume that the compute time is quite heavy. In our case, we noticed that around 70% of our time is spent in memcopy, which for some functions like dot or so might make sense, where you don't have a lot of arithmetic compared to your memcopies. But for something heavy like gemv or gem, that should not really happen. So we've been wondering a bit why that is. And also, if you like kind of remove this 70% overhead to something reasonable, let's say 10 or 20, which is just guessed, but then we should get a decent speed up, right? At least another 2 times faster. So where does it come from? We are not sure yet. So one thing we looked at is first, how does Enzyme for similar use cases like differentiating class with our new rules compare in C against Julia? And the interesting one, we have a lot of plots on that slide, so please excuse that. But what we see if we have the Enzyme C version with the single thread, the performance is quite a bit faster than Julia. Like most of the Julia solutions which we have are here at the top of our plot. C itself is a lot faster. And I mean, if we have some code which is mainly bottlenecked by calling blast routines, there shouldn't be any reason why Julia is inherently slower than C, right? Especially if we use the same blast routines for both C and Julia, they should be on an equal level. And so our assumption is right now that the way in which matrices are represented in Julia is slightly more complicated than in C, because the classical matrix representation in Julia uses a double pointer, like an indirection, whereas in C you just allocate some memory and pass that directly towards your blast routine. So one of the things we do consider now is, since in Julia we get a new matrix type based on, which is slightly simpler, so we would have a single indirection. We would in Enzyme be able to argue better on whether some things will change, will be overwritten, because you can argue a lot easier about the single pointer indirection than about the double pointer indirection. So that's something which we should benchmark in the future. I think it's Julia 1.11, which should introduce it, or 1.12. I'm not completely sure. So, and yeah, in that case, we could hope that with Julia, we catch up to the C versions, which both for like single and multi-threaded are a lot faster right now. So, yeah. Do you have any questions for now, or shall I mention some other outlook? Let me quickly switch back to the audience. Any thoughts on why we might have performance bottlenecks here?
We have one.
So did you figure out where the mem copy is happening? Is that maybe Julia's strange matrix format being copied into something that you can then pass to BLAS? Or why else would there even be a mem copy?
Valentin is laughing, so does he have something to say?
I think the main copy was coming from caching the data of the matrix additionally, because we couldn't prove that it wasn't changed.
Yeah, so to add on that quickly, one of the things that needs to happen, independent of BLAS or otherwise, is if we need a value available in the reverse pass and it's overwritten, we need to be able to save it. The double pointer means that a lot of the alias analysis type of things that we would normally use to prove that this is not overwritten is now, I'm going to say harder, possibly undecidable, which is why having, I think it's Gabriel's working on the better alias info for Julia, but I don't think that's landed yet.
Okay, can you speak a bit closer to the mic?
Oh, sorry.
Thanks.
Yes. Sorry. So part of this is the fact that with the double pointer and the need to cache data, the question as to whether or not this is the same data available from forward to reverse pass is not as easy to answer a question, because the aliasing information is a lot harder, if not undecidable, in the double pointer case. I know there are some folks like Gabriel who's been working on improving the Julia alias information passed down to LLVM and beyond, though I don't think that is landed in Julia yet. Ironically, this is also where some of the discussion that you and Gaurav have really been leading on the question of if we had a say a Julia type that guaranteed that it was never written after the fact, we could also use that for alias information to resolve it.
Any other questions or comments in the room? Apparently not. So if you have more stuff to present, please go on.
Oh, yeah, I just have, I think, one or two more slides. So you can still see my screen, right? Yeah. So yeah, one of the things I was wondering, it's not implemented yet, but if we do differentiate with a certain batch size, what we do right now is we do just, if you say have a batch size of 4, we add multiple GemV calls, and technically you don't really want to have multiple GemV calls, especially if you know that like the memory is next to each other. Instead, you might want to think about what would happen if we have a like matrix multiplication. They could be more efficient, but yeah, it's not really happening right now. It would be a nice optimization, which I would like to see if we can prove that it's correct. But I think in that case, probably Alex, you might want to. We had a similar discussion, I think, in a previous talk about like what would be the right level of abstraction to insert such type of optimizations for Julia. Do you want to like hard code it for specific cases like we have it in Enzyme with like matrix vectors if you differentiate with the batch size, or is there like a more generic approach?
One question, I guess, coming off of that, that this is not actually a question for you. It's more so a question for the audience, specifically people who know about linear algebra libraries like BLAS. So what we found in the past is that, so the even unoptimized version with sort of the 4 equivalent gem calls, if you were not using, open BLAS, but you were using cuBLAS as an example, there actually does exist a like cuBLAS batched like this, even assuming the 4 pointers are distinct. Presumably because, ironically, when any of the sort of like ML libraries implement batched or vector mode of these utilities, you need exactly that there. So we could potentially, even without knowing that these are fused into the same array, do an optimization like that. Obviously, being able to just prove that they're, a gem rather than a gem-v is even more meaningful. But I'm curious if outside of cuBLAS, which just happened to be because we saw this weird API call, be like, why is this taking, oh, that's what it's doing. And it's exactly the same convention, which actually turns out to be really nice. I'm curious if any of, our BLAS or linear algebra aficionados know if any of this is available elsewhere. Oh, wait, one second. Wait, microphone.
I mean, I don't think it would be because I mean in the way that you write a CPU-based BLAS, you actually end up having a what's the word? You end up having a new heap allocation that you then write things to, so that way you can get better cache performance, right? And so what you that's done so mostly because that's you can actually see this in the way that the transpose and the non-transpose end up getting the same performance by doing this, right? But so this batch gem-v is just a matrix multiplication, and so you probably would just represent it as you just build the matrix and then just call the matmul, right? Like they're kind of, I don't see a reason to do the gem-v batch size 4 as anything other than just like a matmul. Given how CPU BLAS is going to be written for GPU BLAS, I don't know if you end up doing I don't know how the internals there, but I mean in open BLAS at least you'd see that there's already that allocation, so you might as well just say, okay, this is the strided matrix I'm going to give you. It's just I'm just going to compose the like this, right?
So the one issue, at least, without being able to get the microphone. Fair. Sorry. So the one issue that we saw, at least in practice for this, is like, first of all, if you can prove that these blocks are contiguous, you should obviously do that optimization and turning it into a matmul. The problem is in the generic batch mode, can this not go out of the? Oh, I'm sorry. I understand. I will keep it closer as I rotate. So the issue though is in many cases when people are calling batch mode, it's not always the case where the 4 different things you're batching over are contiguous with each other. So you may have like different data structures where this is a subslice of a different data structure, which means that you can't necessarily do that because there's no fixed offset between the individual batches themselves to mark as the leading dimension in A or B or whatever else. So they are actually just pointers to unknown memory, which is what CUDA takes for some reason.
Yeah. So what OpenBLAS ends up doing to be able to handle these cases well, right, is it will just take that and write it into, a contiguous buffer, so that way it could do its things nicely, and it will do that behind the scenes. So so it actually always has allocations in there. Now, I think that there are ways to get around this with other BLASs like Bliss, and I don't know how cuBLAS works, so it must be doing something special, which is why it gives a batch interface. But yeah, there's. So I think if you're just targeting open BLAS, I don't think that there's something better to do. But I think if you're targeting Bliss or other BLASs, I think there could be.
But Bliss still needs a stride, and you don't necessarily have equal stride between these vectors. A kind of similar thing shows up with Krylov methods, where you're incrementally creating a larger space, but you don't want to allocate everything up front. And typically the way that's done is to allocate one vector at a time, though due to some GPU specific limitations, really in PETSI, we have added the ability to turn this directly into GemVs, like what had been a multi-dot product kind of interface. It can be turned into a GemV when those columns have equal stride.
Maybe to add a few thoughts. So I think if you have batches, even if you don't know anything about the stride, right, you could still gain performance by just going over your matrix just once, even if the vectors are in completely different places. But the problem is, of course, OpenBLAST doesn't have such a thing. And I think more generally, the functions that are defined by normal BLAST libraries are not closed under differentiation, right? Not everything that you would want to do exists already as a subroutine in BLAS, also not in cuBLAS. So I think what would be really interesting, and I don't think people have really sort of, there's still more work to be done in using things like Bliss or Taco or something where you just extract the linear algebra meaning from a BLAS call, and then figure out on that linear algebra level what should be the linear algebra that we now do in the adjoint, and then how do we generate an efficient kernel out of that, which then depends on the hardware and probably requires auto-tuning and all kinds of things.
If this works, does this work? That's a fair point. Never mind. I was going to make a joke that, since you mentioned linear algebra level and, high level representations of things, this to me indicates, if there were only a linalg dialect in MLIR, that may be usable for representing any of this stuff.
Which that specific dialect is not usable for because it's not BLAS. It's like internals of BLAS with loops, but expressed differently.
Yeah.
Any other questions or comments? Okay, so we are not going to thank Manuel just yet because he's supposed to have another talk. Is it right? Manuel, are you still there?
Yes, I just muted myself to not have any background noise. Okay, yes, I'm there. Shall I just go on with the next one?
Yes, our next speaker is Manuel. With a talk on AD for Rust and the next steps.
Yeah. Can you still see my screen? It's a new window, or do you need to change it?
We still see your Outlook. Now we see ourselves.
Oh, okay. Yeah.
Oh, I'm sorry, you see these boring chairs in the front row.
Oh, okay. So now it works? Okay.
Yep.
Yes. So my second talk is about AD for Rust with the friendly help of your compiler. How do we get things nice on the Rust side? Last year I gave a small intro talk on it, and so this year I'll give it some updates and ask a couple of questions to the audience on further improvements. So first, about my collaborators. Besides the typical enzyme suspects, we have Lawrence, who has been helping me with implementing various different designs which we tried out in the past, and Jet, who is also with us here on the call, and who's been helping me with like documentation, finding too many bugs in my code, and setting up the CI to make sure that we don't introduce new bugs. So first, for those of you who are not really familiar with Rust itself, we do have a couple of AD tools on the Rust side. It's not such a large ecosystem as on the Julia side or so, but I mean, they are growing. Last year, I only presented 2 of them. This year, we already have 4, so it is growing. The main point is on the Rust side, most developers just develop AD at the side if they are developing an AD tool. So most of them, as far as I know, even only support reverse mode AD, because that's what you want to have for your neural network training. Only on the bottom right, offers both forward and reverse mode plus higher order derivatives. So yeah, a couple of features which are maybe nice to know. So as an example, DFDX makes use of the Rust type system. So you get compile time shape checking. So it's not like in Python where you can run your code like a training loop for a few hours. Suddenly it changes to inference because you reach your final accuracy, and now it crashes because you got some shapes wrong. That's obviously not fun. So they have it shape checking integrated, and it then motivates some of the following tools like Raya. So it slowed down a little bit lately. So There are some more tools which we have. For example, Hugging Face has been moving to Rust, especially for the inference part. They also do offer some training nowadays, but they especially use it because they do argue that since it's quite reliable, it's nice to just run the inference on whichever device you have using Rust. And they have a huge amount of examples on nowadays transformers. And for Burn on the top left, it's pretty generic, so it has various backends which can load to PyTorch, to normal Rust matrix libraries, to web GPU, so you can run it in your browser, and they even have other ML and AD tools as a backend. They also have written a blog post lately how to optimize web GPU operations by fusing them, and like they mentioned, they got a speed of 70x. So yeah, it is growing nowadays. It started to exist. So I talked a bit about what changed since my last talk pretty much a year ago. So the first thing is we do have a website now. It's where you find all of our other websites. So it's enzyme.mit.edu, now /Rust for the Rust one. We did transition from a procedural macro, which is a normal Rust macro, into a Rust C built-in macro that gives us a few more insights. For example, normal Rust macros are not able to understand which type to use. They effectively only work on some token streams or strings if you want so, whereas Rust C built-in macros can always, like they're part of the Rust compiler, as you can see already by the name, so they can query additional information. It also has some further benefits, like now we do support cross-compilation, which proc macros do not. We do have enum support, which for Rust is like one of the really basic features because the most common return types are either option. If it's okay if you don't have a result, then you can return an option, which either is some or nothing. Or you have a result type, which either is your value which you want to have or an error type, and creates stability for fixing it. It was quite a creative solution, but I won't go into details this time. We simplified our design a lot, which I'll also show later. We now also get nice Rust-style error messages. As I mentioned, we have cross-compilation support, and we have a proposal accepted to integrate Enzyme into nightly Rust C. It comes with some gotchas, but again. So first, our website. I stole that example from enzyme.jl, so thanks for writing it. Yeah, you can have a look later after my talk. Some sections are still a bit sparse, but please feel free to add or ask questions if you want to consider using it. As I mentioned, we simplified our macro. It doesn't look that nice anymore because on the left side, you can see you could, based on the classic enzyme notation, just put dot for duplicated in front of your argument, and that's going to get passed correctly to enzyme. Nowadays, you need to put all these annotations in the order of arguments in which they show up. You need to all put it inside of your macro, which you put on top of the function. So it doesn't look that pretty, but the argument which we made is now we are Rust C built-in macro, so they're not supposed to look pretty. It's kind of expected that you just have offer full functionality on the Rust C compiler side, and whoever feels like offering a nicer macro, a nicer frontend, can build on top of that. So you can build your own macro, which represents, like as an example, the old design on the left side, and which then gets lowered to the one on the right side. So it makes it easier for us because now we do not introduce any new syntax into the Rust compiler, which obviously compiler developers are really happy about if we like keep it the old way. One note change which we also did, I think on the Julia side they were discussing it, is we have a new name for forward mode AD. So instead of duplicate, you have dual, which just makes it more explicit that it's like slightly different. There are some minor differences. So having a new name makes it clearer for users to point that out. And if you count arguments on the left side, you see in the past you had some const argument for an empty return type because you don't see an error here on the left that indicates the function is not returning anything. So it's comparable to void on the Rust side, C side. So we do not have an activity anymore for that because if there's no return type, why would you put an activity on it? So these are front-end changes for user. The enum support, which I mentioned previously, both of these cases used to fail in the past. Now they do work, thanks to Billy. So an enum is problematic on the Rust side because it can have different types inside. And based on the types, obviously for an AD tool, you do care if you have a float or an integer, because for one of them, it's quite hard to compute a gradient. For the other, it's still hard, but I mean, that's something we can work with. So yeah, we create an enum with like different branches based on the original input value on the left side. We do have a black box which effectively just prevents RustC from like simplifying this whole code. And then we match on our new enum. And if we have an integer, there's not much we can do. We just return a hard-coded constant. And in the other case, we compute x by times x or f times f. So yeah, the gradient here should be 2 times the input. A simplified version on the right side just shows we are also able to accept an enum now at the function border, so you can directly pass it into a function which gets differentiated. So that's also nice on the Rust side. We have proper error messages. In the past, we just used to crash, throw like a stack trace at you and be really unhappy. And now that's effectively what people are used to on the Rust side. What you also get is, for example, on the left side, if you build the Rust compiler without autodiff support, I'm going to tell you about it. This RustC version doesn't support AD. We also have some more checks. As I mentioned, we don't support duplicated in forward mode. We have a new name for it to make things clearer. We have a distinction in reverse mode between active and duplicated. So if you use active for something which you pass by indirection, that's not going to work anymore. People from the C++ side probably know that. And obviously, you want to differentiate functions, not constants or globals or so. So I'm also going to tell you that. There are a few more cases which we add. So yeah, if you want to try it out and you run into a real like internal compiler error, that's a bug nowadays. So please write an issue and let us know. So yeah, with all its improvements, that's actually was only 2 months or so, I think, after my last talk in April. We wrote a major change proposal, which is how you get new features into Rust compiler to integrate Enzyme into Nightly RustC. Nightly is just like our experimental branch. So Rust itself has stability guarantees, Nightly does not. So whenever people would figure out that we are not suited for Rust because we cannot uphold safety guarantees or whatever other issues, they would be able to remove Enzyme again from Nightly. So that's just a test run. And the really nice thing, 2 weeks later, we actually got accepted. No complaints were raised or so. And so that was pretty nice. The only issue is with that, apparently, if you are a new contributor to the Rust compiler and you don't really know how it works, you might start such a major change proposal, and you even get a lot of team members to like compiler developers to accept your proposal, just to afterwards find out that the correct team was not involved. So unfortunately, we need to do it again. So since we have some user-facing changes, there's a language team inside of the Rust compiler which needs to accept all user-facing changes. And apparently, no one realized that that one team should have been involved. So we'll write a new proposal in a few weeks or months when we are ready. So you can't unfortunately use it yet as part of the Nightly Rust compiler. But we did address in the meantime a lot of feedback. So that was nice. We also have ongoing progress. So the first one is benchmarking, because as I showed on the first slide, we now have 4 competing AD tools, probably some smaller ones on top. So yeah, we do want to show that Enzyme actually can uphold its like performance promises on the Rust side. And the typical one is AD Bench. I started porting 2 benchmarks to Rust, which are already running. They even offer a C interface, so we can plug it into the Enzyme benchmark infrastructure. There are some safety checks, because that's what I talked about last year. Effectively, there are some assumptions inside of Enzyme. As an example, if you pass in a duplicated type, a dynamically sized one like a slice or a vector or so on the Rust side, then Enzyme implicitly assumes that your shadow has the correct size. That is, it's at least as large as your primary. And if that's not the case, Enzyme is still going to happily write into a memory location. You might not have allocated that, or it might be a completely different array, which is bad, but Enzyme will nonetheless do it. So that's not acceptable for us. So there are some checks which we can do for dynamically sized types, and I started to implement them on MIR, which is like the medium intermediate representation of Rust. And we do have a couple of, like, I think 20 or 30 optimization and like correctness passes on that level. So it's nothing new. It's not like Enzyme would be unique by requiring certain passes to run on that level. It's just some implementation work which is left. Another progress which we did is create type trees, since Enzyme does need to understand what types you use, and LVM types itself are sometimes slightly too basic. So what you want to do is lower your original source code types or like an intermediate representation of those types into LVMIR, so Enzyme can directly pick it up. Because otherwise, Enzyme is going to run type analysis on your code, which might be slow. And yeah, if you don't provide enough information, it might even fail. So we use the function which you directly differentiated, but then your function which you differentiate is going to call another set of functions for which Enzyme then needs to figure things out. So this is just helping Enzyme to like first compile faster and second be a bit more stable and reliable on the Rust side. So that's obviously a nice improvement once it landed. We do look forward to add some error handling, and as mentioned, we do need TLang approval for integration into Nightly. So yeah, I mean the benchmarks, the two I implemented, but unfortunately I don't have numbers yet. We hope to get to it in the next days. Is bundle adjustment and GMM, Gaussian mixture models. I do intend to implement some more of these in Rust too. So hopefully once we're done with that, we can also hand it over to some of the other AD tools. At least one of them is already interested to like do some performance comparisons to us. So hopefully we can have this chart next year by some earlier time with Rust tools on the right side instead of C and C++ tools. I mentioned the error handler, especially from the C side. I guess some of you know these images, a nice stack trace on the left, and just some enzyme internals going to be thrown at you on the right side. Unfortunately, most Rust users do not really understand LVMIR, and so that's not really helpful. We do, Enzyme itself has some error handler, so we hope to plug it in the future and just maybe write offending failing functions into a file or so they can submit it to us. Now what I want to talk about today is the next feature which we have in mind, which are custom derivatives. We had a talk AD pitfalls last year of effectively there are a couple of reasons why you don't always want to differentiate a function, or like why the result might be surprising. And it's, yeah, so how about telling your AD tool to not differentiate a certain sub-function which is called indirectly, but use a function which you provide for it. That's generally nice and it's supported by a lot of AD tools, but the issue with Rust is really about enabling local reasoning. That's like the typical mantra. And now if you have custom derivatives and you say, hey, don't differentiate that function in like some other package over there, that's not really local reasoning anymore. Like you might get really surprising results if you have your custom rules defined in different crates and they again override things from other crates. So that's complex, something which we need to keep in mind when designing a Rust interface. Yeah, that's something which popped up in one of the enzyme repos a while ago. Someone trying to differentiate this function, which is infamous from Quake. If your 1 divided by square root of x isn't fast enough, I don't think we should do it nowadays, but I mean, back in the time, it was apparently quite fast. So imagine you want to have now some differentiable rendering for Quake or something like that. Then you do need custom derivatives if you were to re-implement Quake in Rust. There are obviously more cases in, like, as an example, numerics, where for stability you have your own motivations for custom derivatives. So we have a solution in Julia, which looks quite nice. So you can check if something is a constant and then like define your custom rule for it. You can check if it's like duplicated or whatever else. The only issue is we don't really do that on the Rust side. We don't have an is-a type. So there's no check which we can do on the Rust side. But it's a nice motivation. You have a single function which you write once, which catches like all of these different cases, whether like a certain input is active or inactive. Because otherwise, if you need to write your own function for like each combination, you just have an explosion of cases. So we have a solution in C++, but we also don't really want that in Rust because you can only use default, correct me, Billy, please, if it's outdated, but I think right now it's still, you can only have default activities, so floats are active, pointers get duplicated, and integers are constant. And then you have some void pointers which you pass around. So that's also not great. We want to have like the flexibility of the Julia side. So how can we do it in Rust? One thing so we are not sure. So that's a question to the audience. Like one example which you could think of is like having, if you define a custom rule, some activity enum on which you can branch. Here it's called match in Rust, but effectively it's just checking which case do we have. And if we have a float, which is const, well, we do not compute any gradient. We just post the original fast inverse square root, which we have down here. if we are active, where we do both, we return the original value and like we differentiate it by like our own user written code. And if you have active only, then you don't compute the original input. So yeah, sometimes you might be able to optimize the right side. That's just one optimization which we could do, like one implementation, but that comes with small runtime overhead because you now have to match on the activities. And in most cases on the Rust side, you should, like we do generate functions. And if you differentiate a generic function, we will create multiple generic, like instantiated functions for you. So that's kind of a new thing because now we introduce the runtime overhead. So it would be nice if we do it with generics, because then we can just like, users can still write one custom derivative, but like based on the branching, we create multiple functions for it, which would have a little bit less overhead, but I'm not actually sure how that would look like. Oh yeah, I should mention generics are kind of like templates in C++. There's some difference, but that's, I guess, the first approximation. And yeah, the other thing I mentioned, now imagine we do have some matrix library under the hood, and we want to construct our own game. So we have 3D graphics and a physics engine. And there are some numerical functions in here which are not like, which we can't differentiate stable. So we do have custom rules. Now both packages implement the custom rule for the same function. They might implement it in a slightly different way. Which one do we actually pick? In Rust, we have a slightly similar case where it's called the orphan rule. So if you want to implement a trait which is kind of like an interface for your own struct, then you either have to define the struct or define the trait. So you need to be out of one of the two packages, which does one of the two. Like something in between wouldn't be able. That works for trait implementation because it avoids having conflicting ones. Maybe we can use something similar for defining custom derivatives. Yeah. So I think Jet had its own thoughts. We discussed a little bit on how we could define custom derivatives in Rust. Do you quickly want to share your thought on how we could design before we ask the audience?
Well, so one of the topics I was kind of discussing is whether we can do this by having traits for like forward diff where it has generic parameters for the activity. And that's a way to me that it would be very natural and like non-magic to implement custom derivatives. I also have like one slide about an example. Let's see. I think that'll be over here. So this is one of the examples that I care about and I've been using as a kind of motivating example for a lot of work I've been doing with Enzyme. The basic structure here is in hyperelasticity and a lot of other physical modeling domains, everything kind of flows from a free energy, which is a equivariant function of its tensor arguments. So this case is simple and the input argument is only strain. And you want to compute things that are related to first and second derivatives of that free energy. Often, like a very common pattern is you take the first derivative and then you multiply by something, and you might want to differentiate that quantity as well. And so it's not a simple second derivative. In principle, you could rearrange things in that way, but it's less efficient to evaluate in that way. And so there's some sample code over on the right, and there's a bunch of tests that all work for that first case. And the stress as written below, which in practice, I wrap this in, like these would be private to the module, and there's a public interface that can be a little more ergonomic, because right now we can only differentiate free functions, but not things like trait methods. Anyway, there are some limitations, like Enzyme, when, say, the matrix B inverse comes out of differentiating the first part. So if you look up, say, over here where the stress is computed, you've got the deep psi dE. That quantity will actually have something multiplied by B inverse that comes out of one of those terms. And the B inverse can cancel with the B that comes right after it. So if you're working analytically, you do that cancellation, and then you actually have to store less data in the first place, or you have to do less computation. It would be nice if we could somehow get that cancellation. But custom derivatives are also needed for a bunch of other things, especially as you go to materials that have like plasticity, which have a return mapping algorithm, which is basically solving a complementarity problem. So it's like a little embedded Newton solve that needs to be done. And so you want to differentiate through that. And this happens at every quadrature point in a mesh. So you're doing, millions of evaluations per second of these kinds of material models. Anyway, that's kind of roughly where we're at right now.
So I think Valentin was just running away, so I can't ask him about the Julia one. But since Billy's already sitting in the first row, do you know about the like plans for the C++ front end? I mean, especially, oh, sorry, yeah, no, just the question for me was, are you going to like generate instantiated like different functions for different combinations of activity based on what users are calling, or do you intend to have some internal branching at runtime because you think the overhead is just not so important?
Yeah, so this is actually a current thing that's being discussed by a bunch of folks, ironically right now led by Sam Misch at Livermore on doing some better C++ interface stuff, which I guess since I happen to be on the laptop that is the other one connected to the Zoom, I can quickly show what's sort of being explored there real quick. Again, this is currently very much in progress, and most of this goes out to Sam Misch, but also like in discussion with Johannes Dofert and a bunch of others on sort of making better syntactic sugar, both for using C++, but as well as also doing custom derivatives. So I'll just briefly say the sugar, which looks honestly remarkably like the both Rust and Julia style of doing things. And again, these are integration tests. They're not meant to be the pretty version, but we have a magic header, include enzyme/enzyme. You have enzyme autodiff. You pass the mode, just like in sort of Julia, you pass the mode. You can specify the activity of the return. And now, sort of unlike the magic ints of yore, which people would often not be directly sent in as a magic int, and then you can't recognize a magic int if it's not a magic number. Now you actually have these as proper types, which also means we can now build the sort of custom rules that take in this type versus that type and so on. Again, the custom rule stuff is still under discussion. Johannes is very much of the opinion that if we just had a single version of the code, we could potentially get away with doing sort of like C++ optimization, which isn't specific to C++, but like inside of LLVM optimization, saying like, we know we're passing an active X, so then we know that this enum is always an int, and then doing the single version like Julia, which is unstable as to the input activity type, would then get co-optimized because we pass in that as a literal. The other discussion, which we're having with folks from Livermore, is like, can we do this as a C++ template, where you sort of imagine a magic template being overridden, and in this case, the template arg is this arg being active or that arg being returned. Obviously, the latter one is a little bit more special because that requires sort of violating the way that one would normally write C++, but of course we are the Clang compiler, so we can interrupt that and make a fictitious template that can be overwritten that we can take in. And again, being the compiler, it really doesn't matter. We can make syntax that looks exactly like Rust if we wanted to inside of C. Compiler is wonderful like that. But this is currently an active area of discussion. And I would, unfortunately, neither Johannes nor Sam are here, but I would heavily recommend we should set up a meeting with all of those folks, just because I think it would be very productive. One other very quick response, though, not actually to the syntax piece, but ironically to Jed's piece on the matrix inverse stuff. So we actually had a talk earlier today an MLAR enzyme, not an LVM enzyme, and thus Rust enzyme available at the moment, but doing linear algebra optimizations, like saying like transpose of X is just X and so on. I don't know if we specifically have one that replaces A inverse A with identity, but we have a bunch there and we should add that if not. This is currently done on the sort of stable HLO MLAR variant, but this is definitely something that we're starting to explore with not just regular LVM optimizations, but optimize everything and have that combine with enzyme both before and after the fact. And Manuel, as to your other talk earlier on just doing linear algebra, that might be a good example of one of the other types of optimizations we want to do in that context. Probably for the sake of pushing that work forward, it would also be useful to have a version where doing that before the code, in addition to after the code, is useful. But regardless, these are the types of things that we also want to explore.
Yeah, thanks. So the issue with matrix inverse is you have a function to calculate a determinant, and the derivative of determinant gets you a matrix inverse, and so the product shows up after evaluating that first derivative, and then we're calculating the forward mode derivative of the product. But in any case, there's unfortunately no like single line you can draw within the kind of structure of finite strain solid mechanics where those derivatives just cancel out like without manually writing out those derivatives. So anyway, I think it's a little bit tricky because like enzyme doesn't have a concept of what is a matrix up front. Like we have a symmetric matrix data structure and write code to calculate a determinant. But that identity does exist. Anyway, there's lots of interesting stuff around there.
Yeah, which I think we should again sit down after this. But I think at least because I don't think this is something that's expressible in the current custom rule infrastructure, just because, right, this is something that, is independent of AD. You always want to have these types of optimizations apply, and that may also require more tree style rotations to be able to get, otherwise commutative terms to be in the right place to be able to apply the equivalent of this pattern. In this case, it's a matrix, so probably not commutative, but the same style, or in this case, associative or whatever else. I think, again, this is an optimization that should be applicable, again, independent of the AD side of things. It just so happens that, by virtue of liking to apply AD on optimized code, we will also go ahead and write the optimization. So it's not it is still the right place to talk about that. But I think probably this is something that is even more general than that we could, again, apply more generically, again, even than AD, but it would also help both the AD generated code as well as AD to generate code.
Any questions or comments in the room? Any questions or comments on Zoom? No comments. Okay, we're running out of time anyway, so thanks Manuel and Jed for being there. Let's have a round of applause they can hear.
Okay. Thanks for organizing.
And we will have 2 more talks after a 2-3 minute pause while we rewire the AV setup.
Or more realistically, a 5-minute pause.